Now, I'm here at Lightwater Valley today for my science project, and I'm hoping to find as many different solids, liquids and gases as possible. So, let's go.
Wherever you go, you're surrounded by objects made of different materials. Scientists like putting things into groups, and one way of categorising materials is to split them up into solids, liquids and gases. Solids are easy to spot.
This metal frame is definitely a solid. Now, it's hard and staying put.
In science, a solid is something which has a definite shape and takes up a fixed volume.
Now, the most obvious liquid has got to be water. It's run it and it changes shape a lot.
Liquids change their shape easily. They simply take on the shape of their container. The most obvious gas is air. Although most gases are invisible, you can sometimes see them inside things.
This thing is full of air. Now, gases can be squashed and are very light.
Just like liquids, gases take on the shape of the container they're in, but they behave quite differently.
Is it on? Yeah. Okay, so I've got two footballs here. This one is full of air. It's light and it's got loads of bounce. And this one is full of water.
Solids, liquids and gases each have different properties which make them suited to different jobs. Solids are often hard and strong. For instance, wood and steel are good for building things with. So why use a liquid in these rides? And why are these dinghies full of air? Solids, liquids and gases behave very differently from each other. Scientists think it's because the particles they're made up of are arranged differently. The theory is that everything is made up of millions of tiny particles, far too small to see. This can is made of solid aluminium metal. Its particles are packed tightly together. They're held in a fixed arrangement and hardly move. Because the particles are held in place, it has a definite shape, unless you're strong enough to change it. Squash all the air out of the can, and you're left with a lump of metal. But the metal itself can't be squashed. Its particles are already as tightly pushed together as possible. It's a solid. The drink behaves quite differently. The particles are still held closely together, but they aren't in a fixed arrangement. Instead, the particles tumble over each other. Which is why a liquid takes on the shape of whatever container it's in. Like a solid, it's impossible to squash a liquid. This bottle's full to the brim. It can't be squashed because there isn't any space between the particles. A liquid can't be compressed. This bottle's full of air. The gas inside can easily be squashed into a smaller space. The particles in a gas aren't held together, and because there's plenty of space in between them, they can be pushed closer to each other. Gases can be compressed. But not every substance fits so neatly into one of these three categories.
All things, all stuff, all bits and bats, all clutter and clatter, it all amounts to three things, the three phases of matter. Liquid, solid, gas. Me, my nails are solid, but blood, sweat and tears are liquid. And as for the gas, well, the less said, the better. Gas. All things, all stuff, all bits and bats, all clutter and clatter, it all amounts to three things, the three phases of matter. Liquid, solid, gas. So what's double whipped cream then, besides gorgeous. It doesn't feel like a solid. It looks more like a liquid. Squirts out of a can and sounds like a gas. Definitely gorgeous, perfect and sweet. But whatever it is, it's great to eat. So what's jelly then? And peanut butter? What's sand in my hand? What's mud in the gutter? What's toffee cream? What's ice cream? It's enough to make a grown man scream! But all things, all stuff, all bits and bats, all clutter and clatter, it all amounts to three things, the three phases of matter. Liquid, or solid, or gas.
Solids don't always stay solid. Heat up these lumps of wax and see what happens. The fact that wax melts means a shapeless lump can be made into a lifelike model with crafted features. Behind the scenes at Madame Tussauds in London, a waxwork head starts out as a model made of clay. Once the sculptor's happy with it, the clay is coated with plaster of Paris to make a hollow mould. Hot, runny wax is poured into it. The liquid seeps into every nook and cranny. After several hours, the wax has cooled and solidified. Eventually, the wax is hard enough to break off the plaster, revealing a lifelike head. Well, it will be with the addition of a couple of eyeballs and a bit of hair. So, what's happening to the wax particles as it melts? In a solid, the particles have very little energy. They hardly move at all. Warm it up and the particles gain energy. Eventually, they have enough energy to break free of the fixed arrangement and move around much more. A solid becomes a liquid at a temperature known as its melting point. These three cones are made up of different substances. They're all frozen in a cabinet which is at -25 degrees Celsius. Linseed oil on the left, water in the middle, and chocolate on the right. At -25, they're all solid, but as the cabinet warms up, the linseed oil begins to melt at about -20 degrees Celsius. It takes several minutes. When all the oil has melted, the temperature of the cabinet is increased. There's no surprises that at 0 degrees Celsius, the ice is the next to go. The chocolate finally melts at 25 degrees Celsius, the temperature of a hot summer's day. Some substances need more energy than others to melt. Aluminium melts at 660 degrees Celsius. Recyclers melt down drink cans and produce huge metal ingots. This one will make 1.5 million new aluminium cans. Even solid rock will melt. Molten lava spurting out of volcanoes is around 1,000 degrees Celsius. Steelworks rely on melting too. Temperatures as high as 1,550 Celsius are needed to melt iron. Solids need energy to melt. Iron needs a lot of energy, but at the other end of the scale, ice needs very little. The energy which makes these ice cubes melt comes from the surrounding liquid. What will happen to the temperature of the drink? A small ice cube needs very little energy to melt. But what about a much larger block of ice? Which will melt first? And while you're thinking about that one, here's a look at ice through the centuries.
In Roman times, Emperor Nero ordered slaves to collect ice from mountaintops. They travelled miles in high-speed chariots simply to cool his favourite drink.
I don't know.
Uh-oh.
I'll have 2 more.
Before fridges were invented, ice was expensive stuff that only the very rich could afford. In Britain, it was cut from frozen lakes in winter and kept cool in underground ice houses until summer. Ice was so rare, it was even imported in huge lumps from overseas.
Look out!
Oh! The first Brit to investigate refrigeration was a man called Francis Bacon. In 1626, he stuffed a chicken with snow to see if the meat would stay fresher longer. But unfortunately, he caught pneumonia and died before finding the answer. In 1916, American businessman Clarence Birdseye pinched the idea of freezing food from the Inuits. He saw that fish buried in ice were thawed out months later and still good enough to eat. Mr. Birdseye had an idea. He started his own frozen food company, and the rest is history. The development of the fridge freezer finally meant that ice became available to everyone.
Whoa!
A few minutes later, and it's obvious that the large block of ice will take many more hours to melt. So, no wonder it was possible to ship ice from abroad in times gone by. Nowadays, we take ice for granted. Before the refrigerator was invented, ice sports could only be played when the weather was cold enough to freeze lakes and rivers. But it isn't long before the surface of the ice rink is chewed up and uneven. This machine repairs the surface by shaving off the damaged top layer and pouring on water. As it freezes, it gives the rink a new, smooth surface. But how is the rink kept cool enough to stay solid? Well, one way of keeping things cool is to put them next to something which is even colder. Liquid nitrogen is extremely cold and has to be handled with care. Place almost anything into it and it freezes immediately. Stretchy rubber gloves become as brittle as potato crisps. A banana freezes so hard, well, you can see for yourself. This is mercury. At room temperature, it's a liquid. What do you think will happen? But keeping things cool by immersing them in liquid nitrogen isn't very practical. On a hot day, you can keep a drink cool by draping a damp cloth over it. It works because the liquid water in the damp cloth is evaporating. It's gradually changing from a liquid to a gas. When a liquid changes into a gas, it needs energy. The liquid in the cloth takes energy from the bottle, so the drink inside cools down. The ice rink uses the same principle. Pipes underneath the ice contain a liquid which evaporates easily. As it evaporates, the liquid takes energy from the ice, keeping the ice cool. When a liquid changes into a gas gradually, like a puddle drying on a warm day, it's called evaporation. When it happens more rapidly like this, we say the liquid is boiling. The particles in a liquid tumble over each other, heat it up, and eventually the particles have enough energy to escape. The liquid breaks up and becomes a gas. In a gas, the particles move as far away as possible from each other. Gases take up far more space than a liquid. In fact, 1 litre of liquid water expands to fill 1,700 litres as a gas. So, what makes popcorn pop? Tiny amounts of liquid water trapped in each kernel suddenly expand. It changes from a liquid to a gas and makes the corn explode. A thermometer in a beaker of vigorously boiling water reaches 100 degrees Celsius. This temperature is known as its boiling point. However hard you heat the liquid, it won't get any hotter. But not everything boils at the same temperature. This is margarine. It boils at around 120 degrees Celsius. Again, the temperature won't get any higher. Liquid nitrogen boils at a much cooler temperature. Even on a tray of ice, it boils and quickly disappears. The opposite of boiling is condensing. This balloon is full of air. Plunge it into liquid nitrogen and firstly the rubber freezes, it becomes crispy. But what's happened to the gas inside? The air has changed from a gas to a liquid. You can see it collecting in the bottom of the balloon. The invisible gas has become a visible liquid. That's what happens when you breathe onto a cold piece of glass. The invisible gaseous water particles in your breath become a visible liquid.
All things, all stuff, all bits and bats, all clutter and all clatter, it all amounts to 3 things. 3 phases of matter. See, you hold a solid cup and you pour the liquid milk. But if you boil the liquid milk in the solid pan, then what comes to pass is neither solid nor liquid, but gas. See, it matters, does matter. Solid, liquid, gas.
To find out how this murky-looking seawater can be made into a tropical environment fit for sharks, and it all happens in the Sea Life Centre just over there.
Inside, there's a spectacular collection of sea creatures from all over the world living in huge tanks. Some species are from the coastal waters around Britain, like these huge cod and bass.
And there's some really weird stuff through here.
Around the corner, the creatures become more exotic. These normally live in the tropics. The tropical sharks are the big attraction, living in a tank the size of a swimming pool.
Shark.
Whereabouts do they live in the wild?
These sharks come from mainly tropical waters. Some of the guys in here are from the Mediterranean. Others are from places like Florida.
Not all sharks are dangerous. The basking sharks, which live in the seas around Britain, are harmless. But these fellas are a totally different kettle of fish. Paul, our diver, needs to be very careful indeed.
What do they need to survive?
Well, these sharks obviously need water. They're tropical sharks, that means the water needs to be at a certain temperature. And this water is heated to approximately 24 degrees C. They also obviously can't survive in fresh water, they need seawater.
The tanks hold huge amounts of it. In total, the Sea Life Centre needs around 20,000 litres of the stuff every day. And the easiest place to get it from is the sea, just over the road. But it's far from clean.
So how do you turn this into lovely clear water like you're swimming in?
Well, this water is passed through a series of sand filters, which takes out a lot of the dirt and bacteria, etc. The water's also passed through what's known as ultraviolet filtration, and that also helps in this process. So what you've got at the end of it is this lovely crystal clear water which fish are happy to live in.
Pipes run from the sea under the beach directly into the basement. The first thing that happens is that it flows through tanks of clean sand to remove any dirt particles. It's impossible to see what's happening inside, but on a smaller scale, it's easy to make your own filter. All you need is a tall funnel packed with sand. Murky seawater has lots of particles floating around in it. To get rid of them, just pour the dirty water onto the sand and wait for a few minutes. Any large particles are trapped by the filter, and clean water drops out at the bottom. It's now much clearer, but is it pure? What else is in seawater? Place a small bowl of seawater on a hot plate. Heat it up and the water evaporates. As the water disappears, what's left behind? Seawater contains salt. You can't see it, but that doesn't mean it isn't there. Add salt to water. Give it a stir and it seems to disappear. It dissolves. Together, salt and water make a solution. Sugar dissolves too. With a bit of a stir, these coloured sugar crystals will eventually disappear. Although the water takes on a slight yellow colour, it's see-through. Solutions are never cloudy, they're always clear. So, what's going to happen with chili powder? Even after stirring, you can still see the chili powder suspended in the water. It hasn't dissolved, so it isn't a solution. This is jelly powder. The crystals soon disappear. As the jelly dissolves, the water becomes coloured, but it's still see-through, so it must be a solution. To understand what's happening, you have to imagine that everything is made up of particles. In every jelly crystal, millions of tiny particles are held together in a fixed shape. They don't move around, they just jiggle or vibrate on the spot. Water is made of tiny particles too, but they have more energy. They move around and tumble over each other. When jelly is added to water, it begins to dissolve. The smaller water particles get in between and eventually separate the jelly particles. A solution is made whenever two substances mix completely into each other. But is there a limit to how much will dissolve? Salt is vital to keep us alive. It's used to make things like soap. Even toothpaste has salt in it. And, in its impure form, it helps to keep winter roads free of snow and ice. Its chemical name is sodium chloride. Worldwide, nearly 200 million tonnes are used every year. Hot countries use the weather to extract salt from seawater. Heat from the sun evaporates the water from shallow inlets, leaving the salt behind. When most of the water has disappeared, the salt is harvested. This outdoor evaporation method has been used for thousands of years, and it's still a frequent sight around the Mediterranean Sea. We simply don't have the weather for it in the UK, but luckily there are other hidden reserves. Rock salt exists in deep underground mines. It's a mixture of clay and salt. But how did it get there in the first place? These underground salt beds began forming in Jurassic times, roughly 200 million years ago. Back then, the world was a very different place. What we now know as the north of Ireland and parts of northern and central England were covered by a shallow, landlocked sea and surrounded by a hot, red, waterless desert. Over millions of years, the water gradually evaporated, leaving huge deposits of salt behind, which eventually became covered by layers of sand. As the layers built up, they became compressed to form rock. Thick beds of rock salt now lie about 300 metres below Northern Ireland, Cleveland and Cheshire. Over the years, water has seeped underground, dissolving some of the salt and bringing it to the surface. Salt water springs bubbling out of the ground were the first clue that salt deposits lie buried underneath.
Nobody knows who first found saltwater springs like this bubbling out of the ground. But when the Romans first invaded Britain, they quickly spotted just how useful these salty springs could be.
You see, Romans knew a thing or two about using salt to preserve meat. Because back then, they didn't have any fridge freezers, so salt became an essential preservative. Although that made everything taste a bit salty. Salty-like.
But more importantly, we need salt to keep us healthy. Every cell in your body needs sodium chloride to stay alive. So throughout history, salt's always been very precious.
Now, would you believe that in Roman times, salt was used as money? Fish and chips, please, Spadger.
Certainly.
Now, sal is Roman for salt. So the word salary comes from the fact that Roman soldiers were actually paid in salt.
About £2.50, please.
£2.50, certainly. £2.50. There you go.
What's up?
Oh, you want a tip? Certainly. There you go, tipped it for you.
To extract the salt, the Romans had used a lead pan like this. Just heat up the spring water. As the water evaporates, salt begins to appear, and lots of it. People often say that too much salt is bad for you, but so is too little.
Bonjour! Now, thousands of Napoleon's troops were thought to have died due to a lack of salt. Pass the salt, one said, and we ain't got none, they replied. You see, their wounds couldn't heal because they didn't have enough salt in their blood. Salt production continued through the centuries, and while the evaporation method may have stayed the same,
What changed was the size of the pan! Salt became big business in Victorian times. Huge iron tanks were used for heating up the salty water. The Lion Salt Works here in Cheshire closed down in 1986. Lying derelict like this, you might think the salt industry has finally died. But today the industry is bigger than ever. Due to modern technology, we can now separate the water from the salt in huge vacuum evaporation tanks such as these. 2,000 tonnes are produced here of British salt every day. Behind me, well, that's about a week's worth.
Ouch! Ouch!
What are you doing?
Rubbing salt into my wounds. How? Have you got any chicks?
Hey?
I've got all this salt and no chicks.
Hey?
I want some chicks. All this salt and no chicks. I want some chicks. I want some chicks.
The word salt is commonly used to describe sodium chloride, but in science there are many other salts too. At a distance, these 5 salts all look fairly similar. They're all the same colour, but each is a different chemical. The 5 salts are sodium chloride, magnesium sulfate, magnesium chloride, calcium chloride, and potassium chloride. The one thing they all have in common is that all over the world, these 5 salts are present in all seawater. Different seas simply contain different amounts. So all you need are the ingredients, a recipe, and you can make your very own artificial seawater.
And that's when I realised that the chicken was still alive. Oh, hello and a big welcome to the Crazy Cook in the Kitchen. Today we go a little daft in the kitchen, like this. He's a crazy boy. Okay, today we're gonna make for you the Atlantic Ocean. Hey, it's got 5 salts. It's gonna be massive.
And I'm gonna make the Dead Sea. It's got 5 salts. It's gonna be bad.
So, first we're gonna start off with the Atlantic Ocean, and for this we got 5 liters of water in a big pan, and we also got 17.5 grams of sodium chloride, salt.
So, I also have 5 liters of water in the pan, and to this water I will add 47.5 grams of sodium chloride. Wow, that's 3 times more than what you got.
So, back to my aromatic Atlantic Ocean, and for this, I'm gonna add 4.3 grams of magnesium sulfate.
And now to my Dead Sea delight, I'm going to add 11.7 grams of magnesium sulfate. Hey, that's 3 times more than what you got.
He's getting a bit too smart for me. I'm gonna show him. I got here 3.4 grams of magnesium chloride.
And in my Dead Sea Dream, I've got 9.25 grams of magnesium chloride. What do you know? That's 3 times more than what you got. In it goes. And whisk.
No, this next stuff is very spicy, so you gotta be very careful. And the spicy stuff in question is 0.9 grams of calcium chloride.
Well, I've got 2.5 grams of calcium chloride. Here you go. Hey, that's 3 times more than what you got.
So, now I'm gonna add just a pinch of potassium chloride, cause in the Atlantic Ocean there's just 0.4 grams of the stuff for every 5 liters of water.
Ha! Cheapskate! I've got 1.1 gram of potassium chloride, and in it go. Hey, that's...
I know! It's 3 times more than what I got.
No, it's a tabletop, you buffoon.
Hey!
If a tomato is dropped into the artificial Atlantic Ocean, it sinks. Take the same tomato over to our Dead Sea, and it floats. The greater amount of salts in the water make it more dense and more buoyant. In the Global Challenge, yacht crews work hard to sail around the world. And crossing the oceans is even harder when you're on your own. More people have orbited the planet in space than have sailed single-handed around the world. And that's just what Andy Hindley is preparing to do. He'll be spending 40 days at a time in this high-tech racing yacht. Like all humans, Andy needs a minimum of 4 litres of water a day. At sea, he's surrounded by water, but it's undrinkable. So what does he do? When he's racing, he can't take much water with him. It weighs too much. The whole point is to keep the yacht as light as possible. He takes only the bare essentials.
Welcome aboard. This is where I spend my 40 days at sea racing. That's my bed. This is my kettle where I cook. This is what I eat out of, a dog bowl. I wash up in this bucket. These are my clothes to keep me dry and my boots to keep my feet dry. Got a toothbrush. Don't really wash, but we use baby wipes to keep clean. And got a bucket, which is actually my toilet.
It's sparse but very sophisticated. GPS, a global positioning system, allows him to stay on course. A radio phone and satellite communications keep him in touch with people back home. Radar helps locate other nearby boats and prevent collisions. But what about the water?
This is probably the most important piece of kit on a boat. It's a water maker. Got a filter here, which takes in salty seawater, passes it out into here, which is pressurised, filtered again in here, and out comes fresh water through this little tube. Then we store it.
Packed inside is layer upon layer of an ultra-fine mesh known as a membrane. It's perforated with minute holes. Seawater is pushed through under pressure, but the holes are so small they only allow the water particles through, leaving the bigger dissolved salts behind. What comes out at the other end is fresh water. Without the water maker, Andy simply wouldn't be able to stay away from land for as long. Another source of fresh water at sea is rain. It doesn't always fall at the right time, but sailors have long known how to use their sails to catch raindrops. In a downpour, you don't even have to drop the sail. Another option is distillation, but it's a bit of a nuisance and takes a lot of energy to produce very little fresh water. And it just wouldn't be practical on the high seas. Imagine trying to boil water and collect the condensation in conditions like these. So, why is the sea salty? Where do the salts come from? Seeing an airship floating high in the sky is a rare sight. Only a few of these graceful giants exist. They use a gas which is lighter than air to stay afloat. As it comes into land, you can see how easily the wind pushes it around. It's the job of the ground crew to grab the tow ropes and help guide it across the airfield. They have to hold on tight, literally stopping the whole thing from floating away. The idea of a lighter-than-air craft has been around for a long time. Before aeroplanes were invented, the first commercial passenger aircraft were airships. The R100 was 215 metres long and one of the first to carry passengers across the Atlantic. It was a huge structure, a rigid metal framework covered with fabric and filled with hydrogen gas. With a spacious interior, passengers enjoyed the same sort of luxuries as those aboard ocean liners like the Titanic. They really were ships of the air. So why did they never become a popular form of transport? This party balloon is full of hydrogen gas. Just like helium, it's lighter than air. But see what happens when a naked flame approaches. Hydrogen is light, it's cheap and readily available, but unfortunately, it's also highly flammable. As the Hindenburg airship came into land in 1937, it caught fire with fatal consequences. 35 people died. An alternative gas which doesn't burn had to be found. These bubbles are full of hydrogen, and although they're light, they easily catch fire. The gas in this bubble is carbon dioxide. It's far too heavy. It won't catch fire, but it'll never get off the ground. This gas is light and doesn't burn. It's helium. Although it's the best alternative to hydrogen, helium is very expensive. It costs £6,000 to fill this three-seater craft, which is probably one good reason why airships are so rare. Every few days the helium needs topping up. It's piped from portable tanks into the airship through a nozzle in its nose. The helium gives the airship lift. Too much lift and it would be difficult to control the airship, so it needs weighing down with bags full of lead. Once up in the sky, the airship floats in an ocean of air. But how does the airship keep its shape? All gases are made of particles. The particles have a lot of energy. They move around and spread out. Gases don't have a fixed shape. They simply take on the shape of their container, in this case, the envelope of the airship. Helium particles bombard the inside of the envelope, but the airship is surrounded by a gas on the outside too. Air particles are constantly striking it. These moving particles create a pressure. Helium pushes on the inside while the air pushes on the outside. But the pressure inside is slightly bigger, big enough to keep the whole thing inflated. What would happen if the helium leaked away? Gases are used to inflate all sorts of things. The gas blown into these inflatables takes on the shape of its container. The more gas that's pushed in, the more particles there are pushing against the inside of the container, and the firmer it feels. The pressure inside the beach ball is greater than the pressure outside, just like the airship. A bicycle tyre needs to be very firm. The more air that's pumped in, the higher the pressure inside. So, what happens if you open the valve? The gas in the tyre escapes until the pressure inside is the same as the pressure outside. Gases always move from high to low pressure. To support this truck, a huge amount of air is forced into each tyre, but it's a slow job. Being able to inflate an object quickly can be very important. A small container of carbon dioxide gas under high pressure is enough to fill a life raft big enough to hold 10 or more people. As soon as the canister is opened, the gas escapes into the raft. Again, it's moving from high to low pressure. All that gas out of this small canister. This life jacket is full of gas, so what will happen if even more is forced in? Why does the life jacket burst? Air is the most common gas of all. Blow into a balloon and it easily inflates. The question is, will a full balloon be heavier or lighter than an empty one?
This one is definitely the heaviest.
I think this is the heaviest one.
This deflated balloon has a mass of 2.1 grams. Inflate it, and how much do you think it'll weigh? It now has a mass of 2.6 grams. Each tiny air particle in the balloon has a mass. One particle on its own doesn't weigh very much, but a balloon contains many millions of them. So a full balloon always has more mass than an empty one. Another property of gases is that they can be squashed or compressed. Compress the air inside this sealed syringe, let go, and the air expands, pushing the syringe back up. In a gas, the particles are spread out. It's easy to squash them closer together. But release the pressure and the particles immediately move as far apart as possible, pushing against the syringe. Compressed gases can act a bit like springs. This awesome ride at Blackpool Pleasure Beach uses compressed air to catapult its riders to a height of 65 metres in just 2 seconds. As soon as the passengers have been safely harnessed in their seats, their combined weight is measured. It's like a big set of scales. The greater the weight, the more compressed air it takes to launch the riders to the top of the tower. The air is forced into a tank and held under pressure, and then it's ready to go. Other fairground rides use compressed air too. The braking systems of many rides rely on air to stop the cars. You can hear the hiss as the compressed gas escapes. What other vehicles have air brakes? Under normal conditions, gases take up a lot of space. During the Second World War, some cars were converted from running on petrol to running on gas, carried in huge bags on the roof. But it's difficult to carry large quantities of gas like this from one place to another, and let's face it, it looks stupid. Today, gases are transported in high-pressure cylinders. The equivalent volume of 300 cylinders of normal gas can be forced into just one by compressing it. So the cylinders need to be extremely strong. All sorts of gases are stored and transported in this way. Different gases have different uses. Carbon dioxide gas is used to put the fizz into fizzy pop. But how did it get there, and just how much gas is there in a bottle of pop? The gas arrives at the POP factory in huge tankers as liquid carbon dioxide. When CO2 is cooled and compressed, it liquefies and takes up less space. So, 700 tankers worth of gas can fit into just this one. In a totally different part of the factory, the cola drink is being prepared. All the ingredients are mixed together in huge vats. The liquid carbon dioxide is transported around the factory through a network of pipes. It's heated up, turned into a gas, and injected into the flat cola mixture. The bottles are filled and capped immediately to keep the fizz in. Because gases are so compressible, it's possible to squash the equivalent of 8 litres of carbon dioxide gas into this 2-litre bottle of pop. This factory produces 1,500 cans of pop and 250 bottles every minute, so you're talking about a lot of fizz. Just think how much carbon dioxide is trapped in all these. We rely on one particular type of gas to keep us warm, cook our food, and even heat things up in the lab. Natural gas is found deep underground, and its chemical name is methane. The gas is trapped in rocks many thousands of meters below the seabed and is brought ashore by underwater pipes. It arrives at one of 6 coastal terminals. When it comes ashore, natural gas doesn't smell. The gas company Transco makes it smelly on purpose, so it's easy to spot a leak. They add an odorant which contains some of the smelliest chemicals on Earth. From here, it makes its long and winding journey around the country. A massive network of pipes transport natural gas throughout Britain. Most of them are hidden underground, but sometimes you can spot their course from the air. Lay them out end to end and they'd be long enough to reach around the world 6.5 times.